When an object is falling, certain forces are acting upon it. In a perfect world, the only force that would be acting on the object and causing acceleration is gravity, otherwise referred to as free fall. In this experiment, we investigated the acceleration due to gravity on 3 spherical objects of similar size and different mass. To do this, we dropped 2 of the objects at a time from a set height, recording their fall and inputting the video into a tracking program. The experiment was then repeated 2 more times, each with a different combination of objects so that there was a visible comparison of all 3 spheres to each other.
In order to calculate the gravitational acceleration, we used the tracker program. First, we placed the video into the program and created a start and end point of the video when the balls were initially dropped and when they hit the ground. Then, we created a scale inside our program. We did so by measuring the distance from the ground to where the balls were dropped. Next, we played the video frame by frame and marked in each frame the center point of the ball. The program used the points we created to create a graph of height versus time. Analyzing this graph, we were able to plot a best fit parabola. Using this parabolic equation, we were able to calculate the acceleration of each ball using the corresponding kinematic equation, y is equal to initial velocity times time plus 1/2 acceleration times time squared. In order to find the gravitational acceleration, we took the value of a in the program and multiplied it by 2. We repeated this process for each ball in each of the 3 videos.
Gravitational force is a field force which affects us and everything we interact with on a daily basis. Because of gravity, we are able to walk on the Earth's surface and not float away into space. Gravity is measured as force just like any other force, in terms of mass times acceleration. This acceleration due to gravity is always directed downwards, perpendicular to the surface of the Earth, and the generally accepted value is 9.81 meters per second squared. Although the mass of an object always remains constant, the local acceleration due to gravity on Earth is subject to change. Acceleration due to gravity is greater at sea level than it is at higher altitudes. The values we measured for gravitational acceleration on the soccer ball were 10.38 and 9.75, for the tennis ball 9.95 and 9.53, and for the basketball 9.42 and 9.49. These gravitational acceleration values are all different and mostly lower than the accepted 9.81 meters per second squared. So what went wrong? One factor which may have contributed to this is the fact that our experiment was performed at a relatively high altitude, decreasing the freefall acceleration. Theoretically, these values should all be the same if the balls were dropped in a vacuum. They were dropped in normal conditions though, so they were all subject to another factor, which caused them to have different and lower acceleration values, and that is air resistance.
Air is comprised of many different elements and different particles, including oxygen, nitrogen, carbon dioxide, and other molecules. When an object is falling, in this case the different balls, the ball is running into these particles and displacing them. Since they are so small in comparison to the ball, the molecules in the air just hit out of the way, but when added all together, these particles are actually able to slow down the ball. This is shown by the video of a circular object passing through the air. How much the ball is slowed down depends on a couple of factors. The first factor is the density of the air. If the air is more dense, then there are more molecules that are hitting it as it falls down. This means that the ball will slow down more than in air that is not as dense, just because there is more to run into. There are strength in numbers. The second factor is the cross-sectional area of the ball. This goes hand in hand with the density. Basically, how much of the object is actually going to come into contact with the molecules in the air. If the object is very small, then very few molecules are going to be hit, and the air resistance is essentially negligible unless falling very far. On the other hand, if the object is very large, it's going to hit many air molecules on the way down and cause the object to be slowed down faster. So based on these factors, we can predict which ball will create the most drag in our experiment. We dropped 3 balls of different cross-sectional radii from roughly the same height in the same air density. So the only real effects on acceleration can come from the drag created by the different ball size and the mass of each ball. Granted, the accelerations can change due to errors in dropping the balls at different times or by not holding them at exactly the same height. But in a perfect experiment performed by calibrated robots, the only effects would be due to the drag. The 3 balls are similar in shape. They are all spheres with no large pieces removed from the material to affect the flight of the balls. Since they are all the same shape, the drag coefficient will be the same for all 3. If the objects were different shapes, then the drag coefficients would be changed because different parts of the objects would be coming in contact with the air molecules. The larger the surface area that would be in contact with the air, the more it would slow down. This is shown by the formula: the force of the drag equals 1/2 the drag coefficient times the density of the air times the cross-sectional area of the ball times the velocity the ball is moving squared. As stated earlier, the only variable that's being manipulated in this experiment is the area of the ball. This can then be brought back to acceleration. Weight is the mass of an object times the acceleration due to gravity. Force equals mass times acceleration, so acceleration equals force divided by the mass. Since the forces in this experiment are weight and drag due to the falling of the object, acceleration is weight minus the drag divided by the mass. However, since mass is included in both the weight and the denominator, these values will essentially cancel out and do not affect the acceleration. So the larger objects would fall slower and the smaller objects should fall faster. In theory, the soccer ball should be the slowest, followed by the basketball, and then the tennis ball. Our experiment did not necessarily reflect this due to errors in the dropping of the balls, manually tracking the center of the ball, and the relatively short fall of the balls, so that this creates the least amount of air resistance. This experiment helped us to understand the air resistance and how it affects the acceleration due to gravity on falling objects.